In this video, we're going to learn how to identify and classify ordinary and singular points of a differential equation. We'll learn why these points matter, define each type, and then work through examples so you can see how to classify them step by step. Let's begin by learning why ordinary and singular points matter. When you're solving a second-order ordinary differential equation, like the one listed here in this green box, you may find that no closed-form solution exists. That means that you can't find a solution using a finite combination of standard operations and functions. Instead, what you can do is look for a power series solution centered about a point x is equal to a. This type of solution is called a Taylor series solution centered at x is equal to a. You may remember studying a series like this in calculus. Whether a power series solution exists and which series method can be used depends on whether the point x is equal to a is an ordinary or a singular point of the differential equation. This is why learning how to identify and classify these points is so important. At an ordinary point x is equal to a power series solution always exists. However, at a singular point x is equal to a power series solution may or may not exist. If the point x is equal to a is what's called a regular singular point, and we'll talk about this in a minute, the method of Frobenius can be used to look for solutions. The next video in this series is going to go over that method. We're now going to learn how to determine if a point is an ordinary or singular point of a differential equation, just like this equation shown here. The first thing that you need to do is put the differential equation in standard form. The equation written here in the green box is in standard form. To put an equation in standard form, all you have to do is divide by whatever multiplies y double prime. The classification of points then depends on p of x, that's just the function that multiplies y prime, and q of x, which is the function that multiplies y. Let's first talk about an ordinary point. A point x is equal to a is an ordinary point of the differential equation if both p of x and q of x are what's called analytic at x is equal to a. This is probably a new definition for many of you, so we're going to go over what this means. A function is analytic at a point x is equal to a if it can be written as a power series centered about x is equal to a. In particular, it has no discontinuity and does not become unbounded at x is equal to a. Let me show you some examples. A polynomial function is analytic everywhere. A rational function is analytic wherever its denominator is non-zero. And then functions like e to the x, sine x, or cosine x are analytic everywhere. You may remember in calculus finding a Taylor series for these types of functions. This next part is really important. At an ordinary point x is equal to a power series solution always exists. Now let's talk about a singular point. A point x is equal to a is a singular point of the differential equation if either p of x or q of x is not analytic at x is equal to a. In particular, x is equal to a is a singular point if p of x or q of x is undefined at x is equal to a and or p of x or q of x becomes unbounded as x approaches a. To help us understand this better, I've written down two functions. This first function has a removable discontinuity at x is equal to a, so it's undefined at x is equal to a. And then the second function, f of x is 1 over x minus a, is both undefined at x is equal to a, and it's unbounded at x is equal to a. Here's the important part. At a singular point x is equal to a power series solution is not guaranteed to exist. If a point is an ordinary point, you can find a power series solution. But if a point is a singular point, you may or may not be able to find a power series solution. Before we walk through some examples, we need to learn one more thing, and that is how to classify singular points. A singular point at x is equal to a is classified as either regular or irregular. A singular point at x is equal to a is regular if x minus a times p of x and the quantity x minus a squared times q of x are analytic at x is equal to a. Remember, p of x is the function that multiplies y prime, and q of x is the function that multiplies y. If x is equal to a is a regular singular point, then the method of Frobenius can be used to obtain at least one series solution centered at x is equal to a. And that solution looks like this. A singular point x is equal to a is irregular if x minus a times p of x or the quantity x minus a squared times q of x fails to be analytic at x is equal to a. If x is equal to a is an irregular singular point, then the method of Frobenius is not guaranteed to produce a solution. I'll go over all of that in my next video. Let's now look at some classification examples. We're going to walk through 4 examples where we are going to identify and classify ordinary and singular points of a second-order ordinary differential equation. To make things easier, I've written down 5 steps that we can follow, and we'll go through these steps one by one as we walk through each example. Our first example is y double prime plus the quantity x squared plus 1 times y prime plus e to the x times y is equal to 0. The first thing that we want to do is put our equation in standard form. Up here on the right in green, I've written down what it looks like for an equation to be in standard form. There needs to be a 1 that multiplies y double prime. Notice in this example, we do already have a 1 that multiplies y double prime, so this equation is already in standard form. The second step is to identify p of x and q of x. P of x multiplies y prime, and q of x multiplies y. In this equation, p of x is equal to x squared plus 1, and then q of x multiplies y, and that is equal to e to the x. In step 3, we need to find where p of x or q of x is not analytic. P of x is a polynomial, and polynomials are analytic everywhere. So we'll say that p of x is analytic everywhere. Q of x is an exponential function, and exponential functions are analytic everywhere because you can write them as a Taylor series. So let's just write down that this one is also analytic everywhere. Step 4 is to classify the points as ordinary or singular. Because p of x and q of x are analytic everywhere, we have no singular points. So what we have to say is every point is an ordinary point. Now let's look at our second example. The first thing we're going to do is put this equation in standard form, so we are going to have to divide each term by x squared. This gives us y double prime plus 1 over x, that multiplies y prime, plus 1 over x squared times y is equal to 0. In step 2, we write down what p of x is and what q of x is. P of x, that's the function that multiplies y prime, and that's 1 over x. And then q of x multiplies y, and that's 1 over x squared. In step 3, we need to find where p of x or q of x is not analytic. P of x and q of x are functions where we have an x in the denominator. This means that these functions are undefined at x is equal to 0. So because of this, they are not analytic at x is equal to 0. So let's say that p of x and q of x are not analytic at x is equal to 0. And because of this, x is equal to 0 is a singular point. Now let's look back up at step 5 because we're going to have to do step 5 for this example. For example 1, we didn't have to do it. Step 5 tells us that if a point is singular, we have to determine if it is regular or irregular. To find if a point is regular or irregular, what we have to do is multiply by x minus that point. So in this example, we have x minus 0, and we need to multiply that by p of x. This gives us x times p of x, which is 1 over x, is equal to 1. This function is analytic at x is equal to 0. Now we have to check x minus a, which is x minus 0 in our case, squared times q of x. This is x squared times 1 over x squared. That is equal to 1. So just like before, we say that this function is analytic at x is equal to 0. Because both of these functions are analytic at x is equal to 0, and x is equal to 0 is our singular point, we say that x is equal to 0 is a regular singular point. And let's go ahead and highlight that. All other points are ordinary points. Let's now look at our next example. I chose 4 examples because each of these examples is different. The first thing we're going to do is put the equation in standard form. So we're going to divide by x minus 1. This gives us y double prime plus 1 over x minus 1 times y is equal to 0. In step 2, we find p of x and q of x. Remember, p of x is the function that multiplies y prime. We don't have a y prime here, so we could just think of this as 0 times y prime, so we can say that p of x is equal to 0. And then q of x, that's the function that multiplies y, and that's 1 divided by the quantity x minus 1. In step 3, we need to look at where p of x and q of x are analytic or not analytic. P of x is equal to 0, so that is an analytic function. So let's just say p of x is analytic. And now let's look at q of x. Notice that if we set x equal to 1, q of x is undefined. So we say that q of x is not analytic at x is equal to 1. So in this example, we have one function that's analytic and one function that is not analytic. In step 4, we need to classify our points. Since q of x is not analytic at x is equal to 1, we say that x is equal to 1 is a singular point. And then let's also say that x not equal to 1 are ordinary points. Now what we need to do in step 5 is classify this singular point at x is equal to 1. To do that, we have to multiply by x minus a, so in our case that's x minus 1 times p of x. This gives us x minus 1 times 0, because p of x is 0. So that's 0. So this is analytic at x is equal to 1. Now let's look at x minus 1 quantity squared times q of x. This is x minus 1 squared times q of x, which is 1 over x minus 1. So this gives us x minus 1. This is a polynomial. So this function is also analytic at x is equal to 1. Since this function and this function are analytic at the singular point x is equal to 1, we can say that x is equal to 1 is a regular singular point. So our solutions are x is equal to 1 is a regular singular point, and when x is not equal to 1, all of those points are ordinary points. Let's now look at our last example. The first thing we want to do is put our equation in standard form, so we're going to divide by x. So we have y double prime plus 1 over x cubed times y is equal to 0. Second step is to find p of x and q of x. Just like in example 3, p of x is equal to 0 because we have no y prime term. And then q of x is equal to 1 over x cubed. Now let's talk about whether or not p of x and q of x are analytic. P of x is a polynomial, so it is analytic everywhere. Now let's think about q of x. Notice that q of x has an x in the denominator. So q of x is not going to be analytic at x is equal to 0. So we'll say that this is not analytic at x is equal to 0. Now in step 4, we need to classify our points. Since q of x is not analytic at x is equal to 0, we say that x is equal to 0 is a singular point. And then the points x not equal to 0 are ordinary points. Now for our last step, we have to classify the singular point as regular or irregular. To do that, we have to look at x minus a, so that in our case, we have x minus 0 times p of x. P of x is 0, so this is just 0. So this is analytic at x is equal to 0. Now let's look at the quantity x minus 0 squared times q of x. This is x squared times 1 over x cubed, and this is 1 over x. This function is not analytic at x is equal to 0. Because this function is not analytic at x is equal to 0, our point x is equal to 0 is called an irregular singular point. And those are our answers. Our answer is that x is equal to 0 is an irregular singular point, and every other point is an ordinary point. And that's it. You now know how to identify and classify ordinary and singular points. You should now be ready to work through some similar problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.